Hello?
Okay, good evening, everybody. And welcome to another session of organic chemistry. For today's session, we are going to start our discussion on Chapter 7, which is concerned with the chemistry of alkenes. But before we go into that discussion, just one announcement to make. The homework assignment, our homework assignment is due on Sunday, this coming Sunday. That is October 13, and that assignment is the our Chapter 7 end of chapter questions. I also want to remind you the next class exam is 2 weeks from today, which will be October 22nd. Okay. Okay, so let us get the session started. Yes. Yeah, that exam will cover chapters 5, 7, and 8. Okay. Actually, what I've done is to roll some of the content in chapter 6 into chapter 7. Okay. Well, I would recommend that you read chapter 6. It will help you, you know. Okay. Okay, so we are going to start our discussion on the chemistry of alkenes. And specifically, we are going to discuss the various aspects of alkene chemistry, including the electrophilic addition reactions, at least for this chapter. And then, of course, we will discuss the nomenclature of alkenes. On this slide, okay, you have a list of topics and or concepts that will be your learning outcome objectives. In other words, I want you to use these topics and or concepts as a study guide for the preparation of all of the quizzes and the exam that you will be taking for this in this particular section. Okay, so the question we want to ask ourselves is, what are alkenes? As you can see here, alkenes are those organic compounds in which you have the carbon-carbon double bond. Alkenes are those organic compounds containing carbon-carbon double bonds. As you can see here, in these examples here, each carbon of the carbon-carbon double bond in alkenes each carbon here is an sp2 hybridized carbon atom, and this carbon also here an sp2 hybridized carbon atom, which is to say that this molecule will be essentially flat, what we call trigonal planar geometry. Which is to say that all of the atoms or groups that are attached to the sp2 carbon atom, they are on the same plane. And that will affect some of the chemistry that we are going to be discussing very shortly. Now, with regard to the orbital picture of alkenes, If we take this molecule here that we call ethylene, we have a carbon atom here attached to another carbon atom, and of course we have this carbon-carbon bond it's a sigma bond, and then we have that carbon is attached to hydrogen through a sigma bond, another hydrogen in a sigma bond, here a sigma bond. Now each one of these sigma bonds here, they are a result of the 3 hybrid orbitals, the 3 sp2 hybrid orbitals, which is to say that on each carbon here we have a p orbital. We have a p orbital here, and in that p orbital we have electron in each one of them, and there also is an overlap, a side-to-side overlap of the p orbitals, in which you could envisage that you have the 2 electrons are being shared by the nuclei of these two atoms here. Okay? And as a result, we say we have, this is a sigma bond right here, and then we say this here is a pi bond, as you can see, this the pi bond is loosely held between the 2 carbon atoms, which is to say that in many of the reactions we are going to encounter with alkenes, those pi electrons will become very important. They will be very reactive. So here, the double bond in the alkene, one is a pi bond and one is a sigma bond. Now we could also think of a possibility of these 2 electrons here. Imagine that these 2 electrons here, instead of being shared by these 2 orbitals, if we draw this arrow, and we will now say those 2 electrons are going to move to the p orbital on this carbon. Now, what do you think we are going to get? The resulting structure will be called what? The resulting structure will be called what? A resonance structure, exactly. I tell you this so you have an idea when we begin to write resonance, what is the genesis of resonance structure? In other words, in order for you to write a resonance structure, there must be available p orbitals for this electron to go into. So what this says is that this here, we have those 2 electrons right here, and as such, this carbon here will be positively charged, and this carbon here will be negatively charged. Okay? So instead of doing this, all I'm showing you here is the orbital picture. Instead of doing that, I could very well just have done this. If I take a look at this molecule here, I could move this to here, and then we have this. Now, ordinarily, I would not expect that you draw the orbital picture unless I ask you to do that. But if I simply tell you to draw the resonance structure, all we are doing here is moving the pi electron okay, that is being shared by two orbitals. Now we're moving those pi electrons to a single p orbital. So this here, if we say this is structure A and structure B, this will be resonance structures. A and B will be resonance structures. Okay, before we leave this slide, I also wanted to let you know here that these two molecules I'm giving you here are ethylene and propylene. These are probably two of the most important chemicals that are made industrially, commercially. Because from these two molecules here, ethylene, you could make a lot of industrial products. The plastic bag that you use for your grocery, polyethylene, is made from there. Polyethylene bags, we use this molecule here to make the polyethylene plastic that are used to make the bags. Also here, we also use it to make polypropylene plastics. And a variety of other organic molecules are made from these two molecules here. And both of them, of course, are derived from petrochemicals, from your crude oil. Okay? So these are very important industrial materials indeed. Okay, so now let us begin to now take a look at the nomenclature of alkenes. Nomenclature of alkenes. Okay, this molecule here with only 2 carbon atoms, this is the simplest alkene with 2 carbon atoms. Of course, the name ethylene, this is a common name that has been accepted by IUPAC as an accepted name by IUPAC. However, if you want to name this using the IUPAC system or the systematic nomenclature, what you do, you derive the name of all of the alkenes from the name of the corresponding alkane. In this particular instance here, the corresponding alkane will be, what will be the name of the corresponding alkane for this molecule with 2 carbon atoms? Ethane, exactly. Corresponding alkane will be ethane. So to name the alkene, what we do, we remove the suffix, the alkane suffix, ane, say suffix, and we replace with the alkene suffix, which is ene. So as you can see here, the IUPAC name for this molecule here for ethylene is called ethene. And the same thing applies to this 3 carbon alkene. The IUPAC name is propene. In the case of this molecule here, also derived from the corresponding cycloalkane, so this is called cyclohexene. You see here, this is the alkene suffix. Anytime you see ene at the end of a name, you know you have an alkene. Now, supposing we have a more complex alkene molecule, just as we have here. To name this, what we do, just as the same set of rules that we gave you for alkanes, we look for the longest carbon chain that contains the carbon-carbon double bond. Keep that in mind. Look for the longest carbon chain containing the carbon-carbon double bond. In this case, The longest carbon chain is 7 carbon atoms, going from here to here. And then we look for the branches or the substituents. Okay, so now we have, keep in mind when you number the longest carbon chain, you give the numbers such that the carbon-carbon double bond will be given the lowest possible number. That is also important. The carbon-carbon double bond should be given the lowest possible number. Okay? So in this case, we start to number from this side, 1, 2, 3. And you can see also here, when you then give the name, you indicate the position of the double bond by the first carbon-carbon double bond carbon. Okay, right here. So we are going to indicate that the double bond is on carbon number 3. And the assumption here is it will be between 3 and 4. Okay? Once you do that, then you give the complete name of the molecule following the rest of the rules of nomenclature. You have a methyl in the 2 position, another methyl in the 5 position. So this becomes 2,5-dimethyl 3-ethene. Okay, so let us do some more examples. Supposing I have this. Say nomenclature continued. Supposing I have this molecule here. Okay, if I ask you to name this molecule, okay, the first thing of course you have to do is to determine the longest carbon chain, right? What is the longest carbon chain that contains the carbon-carbon double bond? 6. Okay, where do you start counting? From here? No, from here, right? Yeah. So you say carbon 1, carbon 2, 3, 4, 5, and 6. That is correct. Notice that we do not go from here to here, saying that is the longest carbon chain in this molecule. No, because that carbon chain does not contain the carbon-carbon double bond. Okay, so therefore, the longest chain here, carbon chain, the parent name for this molecule will be hexene. Okay, so now where is the position of the branch? Substituent, position number 2, right? And what will be the name of that substituent? Propyl. So it becomes 2-propyl. Okay, then you have to indicate the position of the double bond, the first carbon that you get to, which is carbon number 1, 1, hexene. Now supposing we have this. What would be the name of this? What would be the name of this? Longest carbon chain is 8, right? Okay. At this point, it doesn't really, when you do the numbering, because the double bond is equidistant, from each end of the molecule. So it doesn't really matter where you start numbering here, right? So if you say 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so that would become 4 octane. Okay, now supposing we have this. Supposing we have this. Okay, what are we going to call this? And where do we start the numbering? From the left? From here? Okay, why? Very good. Because you want to give the substituent the lowest possible number. Okay? In this case, we want to give the substituent the lowest possible number. So therefore, we start to count from here. 1, 2, 3, 4, 5, 6, 7, 8. So this becomes 2-methyl. Then you indicate the position of the double bond. 4 octane. Now supposing we have this. Okay, so what do we call this? And where do we start the numbering? Let me make it easy for you us to discuss this. Let's say this is A side, and this is the B side, right? Okay, where do we start numbering? From A or B? Where? A is correct. Why A? Alphabetical order, exactly. Okay, now you have to follow alphabetical order. Because no matter what side you start numbering, it will be the same. In that case, then you use alphabetizing order. Okay? So now this molecule now becomes, so this is carbon 1, 2, 3, 4, 5, 6, 7, and 8. So this becomes 3-ethyl, 6-methyl, then you indicate the position of the double bond, 4 octane, now suppose you have the double bond on a ring.
Wait, so what takes priority, the double bond? Like what the double bond?
The double bond is always the focus. You do the double bond first, assign the numbers based on the double bond, then from there all the other are the substituent then comes in. Okay? Supposing we have this. Of course, what will be the name of this? Cyclopentene, very good. Cyclopentene. In this case, you don't need to indicate the number because since we only have one double bond in the ring system, we assume those are in positions 1 and 2. Now, supposing I have this. Supposing I have that. No, let me take this out. Supposing I have this. Okay. Okay, what will be the name of this? What? 1-methyl exactly. 1-methyl cyclo. Now, what if I have this? What if I have this? What are we going to call this? What is? Where's the numbering here? So you start to number from, are you going to number from here to here? No. So keep in mind you give the double bond the lowest possible number. Okay, so this is 1, 2, 3, 4, and 5. So that becomes 3-methyl cyclopentene. Once again, you don't need to indicate the position of the double bond if you only have one double bond in the ring system. Now, supposing we have this. Okay. Now we have 2 double bonds. We have 2 double bonds. Now, whenever you have 2 double bonds, then you're going to have to use the prefix di, and then the suffix in. Okay. Now, this name will be coming from the corresponding cycloalkane. The corresponding cycloalkane will be cyclopentane. So whenever you have multiple double bonds, starting from 2 double bonds or 3 double bonds or 4 double bonds, what you then do, you remove the last Ne of the corresponding alkane and you replace with the diene or triene or whatever. So this becomes cyclopentadiene. Okay? Cyclopentadiene. Now, in this case, okay, let us see here. We have 1, 2, 3, 4, and 5. In this case, we may be able to get away without indicating the position of the double bonds, right? Now, supposing we have this. Supposing we have this. Supposing we have that, yes.
How do you know when the double bonds are in the...
Yeah, that's what I want to get to now. Yes, that's the question I want to have. Yeah, very good question. Supposing you have this. What would be the name of this? At this point, you have to indicate the position of the double bond, because you cannot just say cyclohexadiene. Okay? So you number the double bonds. 1, 2, 3, 4, 5, 6. And so this becomes 1, 4 cyclohexadiene. Okay. So therefore, you could actually then want to do this also here. Say 1, 3, but indeed actually you could get away without the 1, 3, because no matter where it will be 1, 3 anyway. Okay. Okay. So far so good. Now let us go to another set of nomenclature. Yeah.
Can we go back? Sorry.
Go back?
Yeah. With the cycle of hexadiene, why can't you go the other way around and get 1, 3 as well?
1. Wait a minute.
You understand what I'm saying? Like go and count. Yeah, counterclockwise on the one.
Can you go? Let me see. Say with the cyclo with this here. Can we count from here?
No, the other one.
Oh, go from where?
The first one, number 1.
Oh, this here.
No, cyclohexane, and go clockwise from there. So
Go clockwise, right here.
No.
From here.
Yeah, the one counterclockwise.
Oh, counterclockwise.
Yeah.
1, 2, 3. No, you can't do that. But the double bond, you got to include the double bond.
Oh, okay.
You have to include the double bond.
You have to go through.
Yeah, right. You got to go through the double bond.
Okay.
Right.
I got you.
Okay. Okay. Now let us see here. Supposing we have this here, still on nomenclature. Supposing we have that molecule. And also we have this. Now you can see here the carbon-carbon double bond is very rigid. We cannot rotate the carbon-carbon double bond, right? So that gives rise to what we call cis-trans diastereomers. So that gives rise to cis-trans diastereomers. If you recall when we did diastereomers in chapter 5, cis-trans diastereomers. And what are diastereomers? What are diastereomers? They are stereoisomers that are not mirror images. Okay? Okay? So in this case, these are cis-trans diastereomers as opposed to configurational diastereomers. The configurational diastereomers, if you recall, those will contain more than 2 chirality centers. Okay. So now, the name of this, therefore, we call this cis-2-butene, and this becomes trans-2-butene. Now, the cis-trans nomenclature would be fine for a lot of compounds, but there are instances where we cannot use cis-trans designation to describe those diastereomers, cis-trans diastereomers. Supposing we have this. Supposing we have this here, can we make this a cis-trans isomer? We cannot. Cis-trans in relation to what? So because of this kind of situation, therefore, we have to use a new system which we refer to, which you guys already know, using what we call the easy system. Easy system of nomenclature. And when you use the easy system, you then use the can-ingold with the can-ingold pre-log sequence rules. So we know what the can-ingold pre-log sequence rules are. In this case, what do? You take a look at each carbon of the carbon-carbon double bond, focus on one carbon at a time. And then you assign priority to the groups or atoms attached to that carbon based on atomic number. So here, bromine is A and fluorine is B. And then we come to this carbon, we assign priority again. What will be A? Which is A? Chlorine, right? Okay. And the carbon here is B. Okay, now, you then take a look at what you have. If the two priority groups, the two higher priority groups, or the two lower priority groups, are on the same side of the molecule, then you say same side of the carbon-carbon double bond equals to Z. That would be your Z isomer. If it's opposite side, if they are opposite side, that would be your E stereoisomer. So in this case, we have the A and the B, and the A are on opposite side, right? Okay, so what would be the stereochemistry of this carbon-carbon double bond? E. So this becomes E. So therefore, how do we name this? How do we name this? So this becomes paren E. Since we only have one double bond in the molecule, we do not need to indicate the number. So it becomes E. What's the rest of the name? What the rest of the name? Bromo. One bromo, right? Is that right? One bromo, one fluoro, two chloro, one fluoro, right? In alphabetical order. And what is the base name? What's the base name? Propene. How many carbon? 1, 2, and 3. Okay, so that becomes 1 bromo, 2 chloro, 1 fluoro, propene. In the case of propene, you don't need to indicate the position of the double bond. It's only 3 carbon atoms. So let me make some room for myself here and write it. So that becomes E 1 bromo, 2 chloro, 1 fluoro, propene. Okay. Now, supposing I ask you to give me to write the Z isomer, what will it look like? The Z isomer. What would the Z isomer look like?
Put the C screen and see how.
I will just do this. So the fluorine will be here and the bromine will be here. And that will be the Z isomer.
Yeah, that's what I asked.
Right? Well, as long as you put the this is B at this point, as long as the same priority are on the same side. You know, this is priority B and priority A. Okay, it doesn't matter which one you switch. Okay. Now, let us do another one before we go to another topic. Supposing we have this. Supposing we have it. Okay. Can you give the name of this, including the easy stereoisomer? First, let us assign priority first, right? Let's look at this carbon. Which is priority 1? I mean, priority A? The top one. Very good. So this is A. And this is B, and if you look at this here, this is A, and this is B. So therefore, this will be what?
E.
The E. So I will leave you to give the rest of the name. So this will be your E isomer. Now, let us do a little bit more, introduce a little bit more complexity to this. Okay. Yeah, we could do this. This should be easy for you guys to do, right? So we don't need to worry about this. Okay, let's do this for you.
You don't know that.
Okay, let's do this. I already have it here. I got the name here, Z4-ethyl. Okay. Okay, so let us do that. Just okay. Focusing on this carbon here. Priority. This is A, and this is B. I'm focusing on this carbon here. This is A, and this is B. So you can see here, the name of this is, the stereochemistry is Z, and you have, the longest carbon chain is octene, starting from here. This is carbon 1, 2, 3, 4, 5. Oh, I'm sorry. Sorry about that. Let me take that back. This is 1, 2, 3, 4, 5, 6, 7, and 8. So the longest carbon chain is 8. And the double bond is in position number 2. As you can see here, 2 octane. Okay, and therefore we have Z4-ethyl because the ethyl is in the 4th position. This here is in position number 4. That is your branch or subsequent. It's in the position number 4. So we say 4-ethyl, and then we have in position number 3 and 7. we have methyl. This is a branch or substituent in number 3, and in position number 7 we have another methyl. So therefore we said Z4-ethyl 3,7-dimethyl 2-octane. Okay. Okay, let us see whether you can do this next one here.
Can you go back really quick, please?
Go back? Okay. Yes. Huh?
He said he's going to leave us to do it.
Yes. Give that name. Okay. Okay, number 10. Let's go to, I'm sorry, page 10 on my slide here. Okay. Let us do this. Let's do this. Now that we have 2 double bonds in this molecule, let's do that. The first thing we need to do is to assign the longest carbon chain. It's kind of cold in here. The longest carbon chain, right? Now, what is the longest carbon chain? We have to start with number from here, or from right or from left?
Right.
From right? Okay. So this is 1, 2, 3, 4, 5, 6, 7, and 8. Okay, what we need to do now, we need to name this molecule, which is to say that the first thing we need to do, we also need to assign the stereochemistry, the easy stereochemistry for the carbon-carbon double bond. Okay, so let us do that.
Which carbon-carbon double bond?
We have 2 carbon-carbon double bonds here. Okay? Okay, let us focus on the first one here, the carbon-carbon double bond between carbons 2 and 3. Let's focus on carbon 2 and assign the priority. This is A, and this is B. Then we come to carbon number 3 and assign priority, right? So this part of the molecule here, this would be A, and this would be B. Okay? So what is the stereochemistry of this carbon-carbon double bond? Okay, that is Z. Okay, very good. Then once you do that, then you come to this double bond here. Okay, now let us focus on carbon number 4. Okay, when you focus on carbon number 4, which is the priority here? This double bond or this methyl? Double bond, very good. So this is priority A, and therefore the methyl is priority B. Then you come to carbon number 5. Okay, then we assign priority again, which is priority A. This here A, and this here B. So therefore, what is the stereochemistry of the double bond between carbon 4 and 5? Okay, very good. Did you say E? Okay, very good. So therefore, this is E. I see you guys got the message here, I think. Okay, so that is E. So now let us name this molecule. Now we have to name this molecule. Let us identify the substituents. Okay, this methyl is in position number 4. It's a substituent. Okay, another methyl in position number 5. Substituent. Let me take this. Is there any other substituent? No? Okay, very good. So now let us name this molecule. We have double bond in position 2. The stereochemistry is Z. So we say paren 2Z, comma, about the double bonding on 4. is 4E, right? Say 4E. Close the parent. And then we give the name of the substituent. This time is 4,5-dimethyl. 4,5-dimethyl, the longest carbon chain, and the double bonds are in positions 2 and 4, right? Okay, so it becomes 2, 4, octa, okay, octa, diene, and that is the complete name for that molecule. So when you have a problem like this, you know you are going to get problems like this in your quiz and your exam. Of course, identify the longest carbon chain, identify the priority, assign the stereochemistry E or Z to the double bonds, and then give the complete name, taking account of all of the substituents. Yes. The double bond on carbon 4? Okay. Why will it be what? Oh. Okay. Let me go back. Okay, you got the name here. Let me. Okay, the question you are asking on this carbon here. Okay, which priority is A and which is B, right? Okay, we say this here. We say this group here, this group is A. And this here, we say this is A. And we say here, this methyl is B. You see why? Okay, that's right. Okay. Okay, now I want to change gear a little bit. And we discuss, what time do we have? Let us discuss the index of hydrogen deficiency, or what your book will refer to as the degree of unsaturation. To do that, let's a little bit of background information. If we have this, that is an alkane, right? Mm-hmm. What is the formula for that alkane? The formula is C4, we have 4 carbon atoms, right? H10, right? We call the alkane saturated molecules. Because all of the bonds in the alkanes are, of course, are single bonds, and they have the highest ratio of hydrogen to carbon atoms in any given molecule. In other words, you have the full complement of hydrogen that you could have in any compound relative to hydrogen and relative to carbon in any given compound. Keeping in mind that carbon, of course, in this particular instance, carbon has only sigma bonds. So we say the alkanes are saturated molecules. You cannot have any more hydrogen in this molecule. Now, supposing then I have this. Let's give the molecular formula for this molecule here. This is 2-butene. It's C4H8. How many hydrogen lengths do we have in this molecule? How many? 2. Which is to say that because we have a double bond, each double bond we have in this molecule takes away 2 hydrogen atoms. Do you follow that? Each double bond that you have in the molecule takes away 2 hydrogen atoms. Now supposing that I have a cyclobutane, this here. Supposing I have a cyclobutane. What is the formula for cyclobutane? C4 88. In other words, cyclobutane and butene are isomers. What kind of isomers are they? Butane, this is cyclobutane, and this is butene right here. And this is cyclobutane. What kind of isomers are they? Constitutional isomers. Because the attachment of the difference between them is that you have different attachment of atoms. So if I give you this formula, I say give me all of the constitutional isomers from this formula. You have to include the alkenes and the cycloalkane. Because in this case, as you can see here, for each ring that you have, how many less hydrogen do you have? 2. So each ring takes 2 hydrogen atoms less. So that is why I call this index of hydrogen deficiency instead of degree of unsaturation. Because you cannot say cyclobutane is unsaturated. Cyclobutane, we cannot really say it is unsaturated because it does not have a carbon-carbon double bond. All of the bonds are single bonds. So therefore, we say these molecules have the index of hydrogen deficiency. In this case, index of hydrogen deficiency for butane, we say cyclobutane, we say is 1. The index of hydrogen deficiency for butene, we also say is 1. So for each index of hydrogen deficiency, it's a ring or a double bond. Yes.
So the long chain and the cyclo, you say they all have single bonds basically. Hydrogen deficiency is based off the long chain one. It's just based off the maximum amount subtracted from.
No, the hydrogen deficiency is based on relative to the alkanes, the straight chain alkanes. Okay? I mean, all of these are relative to the straight chain alkanes. And that is why I gave you the butane earlier to use for reference. That is your benchmark. Okay? The alkanes do not have any hydrogen deficiency. Okay? Okay. Now, what I've done here, I've given you a formula here. Please, you need to know this formula because this is not in your book. The system your book tells you to use, if you want to use that system, that is fine with me. But I think this formula here will works better than what you have in your book. And what does this formula tell you? It's the index of hydrogen deficiency, IHD, equals to the number of carbon atoms in the molecule minus the number of hydrogen atoms divided by 2 minus the number of halogen. In this case, the halogen will be bromine, chlorine, or iodine divided by 2 plus the number of nitrogen atoms in the molecule divided by 2 plus 1. Okay, use this formula all the time. Now, if you have a very simple formula, it is quite possible that you don't need the formula. But if you have a very complex molecule, in other words, if you have a very simple molecule, you may not need this formula. But if you have a complex molecule, this formula comes in very handy. Okay, let's do a couple of problems.
Wait, can you go back?
Please.
Huh?
Can you go back?
No, it's the same formula here. The formula is here.
The variables.
Oh, okay, I see, okay.
Oh, okay. The
carbon is the number of carbon atom, hydrogen, number of hydrogen atoms. The X is for the number of halogen, which is bromine, chlorine, and iodine. And nitrogen, the N is the number of nitrogen atoms. Okay? So let us do a couple of problems. So calculate the IHD of a molecule having the formula C6H6 is oxygen. Okay, if you use this formula here, this case, number of carbon atom in this formula they have given us is 6, and that's what we have there. Then the hydrogen divided by 2, number of hydrogen is 6, divided by 2 is 3. You do not have any halogen, so that's 0. No nitrogen, that is 0. Then plus 1. So the IHD is 4. So if we say we have an IHD in the molecule that of 4, what does that tell you? What information does that give you? What does that mean? 4 double bonds, okay. Or 4 rings, okay. Okay, all kind of combination, right? Or it could also mean a triple bond. It could mean a triple bond, carbon-carbon triple bond. Because the carbon-carbon triple bond gives you an IHD of 2. Okay? The double bond gives you an IHD of 1. The ring gives you an IHD of 1. So therefore, if you have an IHD of 4, you could have a combination of rings and or double bonds or triple bonds. Okay, so now let us do this problem here. Supposing I give you this formula, C6 H4. You have nitrogen. Now let me put that out. Let me put that out. Loading in there somewhere. Chlorine, nitrogen, and oxygen. If I give you that formula there, and I say, give me the index of hydrogen deficiency for this molecule. Okay, let us use this formula here. Let us use that formula, okay? So, here, using the formula IHD, you see equals to number of carbon atom is 6, right? About number of hydrogen is 4, so 4 divided by 2, that is 2, right? How many halogen do we have? 1. So that is 1 divided by 2, that is 0.5. How many nitrogen do we have? 1. Okay, so that's plus 0.5 for nitrogen, and then plus 1. Okay? If you do that, of course, this cancels out. Minus 0.5 plus 0.5, that cancels out. Okay? So what do we have here? We have this here, 6 minus 2, that is 4, plus 1. So the IHD for this is 5. The IHD for that is 5. Okay, actually, what I wanted to give you, this molecule is actually, I will give you the structure of this molecule, is this here. Notice that the oxygen doesn't come into the calculus here. Okay, so the IHD for this molecule is 5. And this is actually this molecule here. That is that molecule. Okay?
Yeah.
Thank you.
How do you know it's a ring?
Huh?
How do you know it's a ring?
How do I know?
It's a ring. Yeah.
Oh, no. When I made up this this problem here, I'll use this here. It could be any other, it could be some other molecule, but what I'm saying is it is consistent with this molecule.
Okay.
If you look at this molecule here, okay, the ring is 1 IHD, right? And each double bond is 1 IHD, so that is 4. And then the nitrogen-oxygen double bond is another IHD, okay? And that is 5. And that's how you got 5 right here. Okay?
Wait, question.
Yes.
4?
No, it's 5.
It's 3 double bonds in the ring, and then it's a double bond. Oh, because the actual ring.
Yes, you have the nitrogen-oxygen double bond also. Okay. Anyway, that is how you use the index of hydrogen deficiency to narrow down the possibilities if you are dealing with some unknowns. So at this point, what I want to do, I want to introduce to you the 4 major types of organic reactions. Oh, can you calculate the IAG for this? I'll leave that for an exam. So I didn't want to show you that, but since you've seen it, you should be able to calculate the index of hydrogen deficiency for this molecule. Exactly. You see how easy it is? You see, just count the ring and double bond. You thought it was that difficult. What ring is? Okay, that is so. This is 13. IHG for this molecule equals to 13. Okay. You see it?
Yeah.
Okay. But if I gave you the formula and I say calculate the IHG, then you don't see this structure. You have to do the calculation.
Yeah.
If I give you the molecular formula for this molecule, then you have to do the calculation. Okay.
Yeah.
Okay, now let us take a look at the different types of reaction that we encounter in organic chemistry. Because we are very soon going to get very heavy into reactions. See, what we want to let you know at this point is that even though organic chemistry involves a lot of chemical reactions, most of the reactions actually come under a few categories of reactions, just as you see in this particular slide. So you have 4 major types of organic reactions. And most of the reactions that we encounter, we could actually categorize them under each one of these categories of organic reactions. We have what we call the addition reactions. In the addition reaction, if you take a carbon-carbon double bond, just as we have here, what are we doing? We are adding hydrogen bromide, reacting hydrogen bromide with a carbon-carbon double bond. In essence, what have we done? We added hydrogen and bromine across that carbon-carbon double bond. We will give you the mechanism of this reaction later. Okay, we told you earlier, the pi electron in the carbon-carbon double bond is very reactive. So we are going to be using this pi electron here. You notice we start those 2 carbon atoms, they are sp2 carbon atoms, and we end up with 2 sp3 carbon atoms. So we say this is addition. So therefore addition is what? When you have 2 molecules, you join them together to form 1 molecule. That's an addition reaction. The next category of reaction is what we call substitution reaction. Most of these names actually do explain themselves. An example of a substitution reaction here, what are we doing here? We are replacing one of the hydrogen in methane with a chlorine atom. Okay, I believe we've done this before. We react this molecule with chlorine in this case, or sometimes with bromine, in the presence of light. In essence, we are replacing one of the hydrogen with chlorine atom to get this product right here. So we say this is a substitution reaction. Then we have what we call elimination reactions. Elimination reaction. In the elimination reaction, what are we doing? Can anybody tell me what we are doing here? We are removing a small molecule from a bigger molecule, right?
Where do two hydrogens come from?
This here?
Yeah.
They are here.
Oh, okay.
Okay. So in essence, what are we doing here? We are eliminating the element of water from this alcohol. It's almost as though you're pulling out this hydrogen and this hydroxyl to form water, and in so doing, we now form a carbon-carbon double bond.
It's going to always be eliminating water.
No, not what. This is just an example. Anytime you see you removing one small molecule from a bigger molecule, just elimination reaction. Okay. And for here, you can see here, it's almost the reverse of addition reaction. We are going from an sp3 carbon, we are forming two sp2 carbons. Okay, so that is the elimination reaction. And then finally, we have what we call rearrangement reaction. In the rearrangement reaction, all we are doing here is rearranging the molecule. Okay, what do we have here? We start with this alkene. Okay, this is one butene, starting with one butene, and in the presence of some kind of acid catalyst, we are now forming two butene. In other words, all we've done here is just to rearrange this molecule so that we move the position of the double bond. Okay? Move the position of the double bond. Okay, so these are the four major types of reactions you have in organic chemistry. And we are going to be using a lot of these as we go along during the course of this semester. Now, before we end our session today, let me now start with the first set of reaction, which is the addition reaction. We've got plenty of time. Okay, I will leave you with this. Let me just introduce this very briefly. Let us start with addition reaction. I will give you just a few examples, and when we come back, we will then begin to give you the mechanism of this reaction. In other words, we simply show you the outcome of this reaction, then when we come back on Thursday, begin to show you how do this reaction actually occur. Okay? For example, if I have this, I have this. In this case, hydrogen bromide. If I say, I give you this cyclohexene, I give you hydrogen bromide, I say, give me the product of this reaction. Okay? What it does, this is addition reaction. we have here.
Yeah.
Well, in this particular instance, yes. In the addition reaction, we are adding, if I say what type of reaction is this, this is addition reaction. You're adding hydrogen bromide to this carbon-carbon double bond. Now, let us add a little bit of complexity to this. Supposing I do this. And I give you the same starting the same reactant, hydrogen bromide. What will be the product? What will be the product? I will tell you right now. The product is going to be this here. The hydrogen will come to the carbon that has more hydrogen. The hydrogen will go to the carbon that has more hydrogen. And the bromine will go to the carbon that has less hydrogen. So therefore, we call this type of reaction a regio-specific reaction, because the reactant goes to a specific position on the carbon-carbon double.
You like that?
We call it a regio-specific reaction.
So adding the hydrogen and bromine takes off the double bond, right?
Yes, in other words, addition reaction. Once you add, the double bond is gone. You go from sp2 carbon, you get sp3 carbon.
It's like, it says regio?
Yes, regio-specific reaction. Because the reactant, in this case, hydrogen goes to a particular position on the carbon-carbon double bond. The hydrogen goes to the carbon that has more hydrogen. And we also refer to this as what we call a Markovnikov reaction. Markovnikov, we call it a Markovnikov addition reaction. Because in the Markovnikov addition reaction, the rule is, if you are adding hydrogen and any other atom across a carbon-carbon double bond, the hydrogen will go to the carbon that has more hydrogen. Okay? Let me write it. Let me write it down for you. For Markovnikov reaction,
Are they the same thing?
huh? Yes, yes. Markovnikov reaction is a regio-specific reaction. Okay. Okay, simply means that here, hydrogen, whenever, okay, let me say this. When adding hydrogen and some other atom across a carbon-carbon double bond, the hydrogen goes to the carbon that has more hydrogen. It's almost like the case of the rich get richer. And we call that a Markovnikov addition reaction. Okay? We call that the Markovnikov addition reaction. So I think, let me see here. Anyway.
What if they were both CH3?
Huh?
What if they were both CH3? What if
CH,
they both had the same amount of hydrogen?
but then you get a mixture. You get a mixture of products. Okay, so folks, when we come back on Thursday, we are going to continue with this. With this particular type of reaction that we have just given you here is what we refer to as electrophilic. I'll tell you why we call it electrophilic addition reaction.
Right now?
No, not right now. We call this electro. So when we come back, we explain to you why we call this electrophilic addition reaction. Okay? Okay, so we'll see you on Thursday.
Can you explain the three GL specific reactions?